Hello, this is Ms. Eisencraft with Task 3 for Chapter 10 review. Significant tests for difference in means. So, in a study of heart surgery, one issue was the effect of drugs called beta blockers on the pulse rate of patients during surgery. The available subjects were divided at random into two groups of 30 patients each. So, there's your N if you're ever going to need it. Probably N sub 1, N sub 2. Okay. One group received a beta blocker, the other group received a placebo. The pulse rate of each patient at a critical point during the operation was recorded. Now, the treatment group had a mean pulse rate of 65.2 and a standard deviation of 7.8. For the control group, the mean pulse rate was 70.3 and standard deviation was 8.3. So we only have the standard deviation of our sample. We don't have it of the population. So we are going to use a t distribution, and that, whenever you see means, it's going to most likely be a t distribution. Okay, because the formula that we're using to calculate is the standard error, not really the standard deviation. So it's a little off. Okay. So kind of looks like the normal distribution, but a little bit more in the tails. Okay, so let's just keep going. So these are stats here. So we have a sample mean from group 1 that received the treatment, right? And they had a mean pulse rate of 65.2. And the standard deviation of this group was, this sample was 7.8. The control group, the placebo group, the sample mean for them was 70.3 with a standard deviation of 8.3. So this was the treatment, people that received the drug, and this was the placebo. So it's always a good idea to stop and think about what the heck these numbers mean. These are stats. They didn't give us a table of everybody's and then make us enter it in a list. They already averaged them. So it looks like the treatment, our sample is showing that our treatment group has a lower average pulse rate than our placebo. But is this significant? So you can even just subtract it, like, well, how much? Like 70.3 minus 65.2. It is lower. It's like 5.1. The pulse rate is 5.1 lower. Is that significant? And you have to take into account this, or you let the calculator do all the magic. So let's first of all do our, we want to test the hypothesis that beta blockers reduce mean pulse rate. Okay, so the null would be that there is no difference in the true population. So Muse aren't that good today. So sorry. The alternative is that the beta blockers, so the treatment, reduce the mean pulse rate. So we are hoping that mean 1 minus mean 2 is less than 0. Because we want this to be higher, the placebo to have a higher pulse rate. We want this to be lower. Okay, so there you are. There's the hypotheses. Okay, so use your calculator to find the test statistic, which is going to be a t-value in this case. It'll also do a calculation. It will do a degree of freedom. You could conservatively use 29, but the calculator does, which is really conservative and a little bit more rough, but the calculator will do another sort of complicated calculation for you. So let's go ahead and enter it. So we're going to go, this is means, and there's 2 of them. So we're going to go to stat test, 2 sample t-test. So that is number 4. Okay, and we have stats, an X1, X bar, the mean pulse rate for sample 1 was 65.2 with a standard deviation of 7.8 and a sample size of 30. The second group had a mean pulse rate of 70.3, standard deviation of 8.3, and also a sample size of 30. We are testing the alternative that M1 is less than M2, so the middle one. Just say no to pooled, and let's calculate first. Degrees of freedom, the calculator did some magic formula, 57.7, and they got a t-value of -2. That's pretty far away. Well, but it is a t distribution. So that means a little bit less than it does on a z distribution. Okay, let's calculate it. And there's the p-value. Okay. So let's stat test 2 sample 2 test. Let's draw it. Okay, so we're way over here. 2.45 standard deviations away on the t distribution, which is a probability of 0.0086. Right, there's the null. The R difference has a t value way over here. A very small probability of that happening if this was true. So since we have a very small probability of this happening if this was true, then we can reject this and say, well, we don't think this is probably true then, because this is so unlikely to happen. So since P equals 0.0086, which is less than alpha at 0.05, we reject the null. We have convincing evidence. That the true mean pulse rate for those that take a beta blocker is lower than those who receive a placebo. I guess you could just say we have convincing evidence that it lowers pulse rate. All right.